So yesterday we went through the beginning of thermodynamics, energy and its changes, work versus energy. Work is a force exerted over a distance. Specific heat capacity. Apparently, I don't even know if we touched that. I don't think we got to that. That's more of today's discussions. So let's take a look at page 6 in this note packet. Start there. All right, so here we have a sidearm flask. We have a piston. If we take a look, if we drop this zinc into that, that's going to produce a gas, and that gas is going to do work on this piston. What we want to keep in mind when we look at these type of problems is the signs and stuff that basically tell us the positive or negative, whether the well, let's just look down here. This is the easiest way. Positive signs, so work is done on the system. That means you're putting energy into the system. The system gains heat. There is a net gain of energy by the system. If we're looking at delta H with this, and this is positive, that means basically it's an endothermic reaction, meaning that if we were to look at reactants versus products, it would be reactants plus energy yields products. So that would mean that if delta H is positive, the products have more energy than the reactants. And that's kind of counterintuitive because we have energy written out here. That's just it. If you're walking along and you see money, you pick up the money. The money's no longer out there to be seen. Same thing here. The reactants are gaining this energy so that the products have it. That's why we don't see the energy here. For this reaction, delta H would be positive. The opposites are true when the sign is negative. If it loses heat, work is done by the system. In this case, work would be negative because the system is doing work. A net loss of energy by the system. Exothermic reactions would be the opposite of this. So basically you would see reactants yield products plus heat. The weird thing is that when we're doing these, a lot of times we're using a thermometer to measure these things. Keep in mind that the thermometer is not part of the system. It's part of the surroundings. So if we notice that the temperature of the thermometer is getting higher, that means that the system is losing energy. If we notice that the the temperature on there is getting lower, we notice that it is absorbing energy. So the system is absorbing energy if the thermometer is going down, and the system is losing energy if the thermometer temperature is going up. If we take a look here, units of energy, we know a thermometer measures temperature, which is average kinetic energy, not heat. Calorimetry is the science of measuring heat. We have something called the heat capacity, which basically is the amount of energy to change the temperature of an object 1 degree Celsius. We have something called the specific heat capacity, which is more specific than that, and that's the amount of energy required to raise 1 gram of a substance 1 degree Celsius. So that's the specific heat capacity. For water, 1 lowercase calorie is the amount of its specific heat capacity. 1 uppercase calorie is actually what we call a kilocalorie. So if we take a look here, One lowercase calorie is equal to 4.184 joules. So the specific heat capacity of water is either one lowercase calorie or 4.184 joules. Now you notice the units on this? Again, it's per gram degrees Celsius. And you learned in your gas laws you needed to change the temperatures to Kelvin a lot of times in that to deal with the absolute value scale. With this, since one change in 1 degree Kelvin is equal to one change in 1 degree Celsius, you can actually use Celsius. So if we take a look, if we want to measure the amount of energy, we can take the specific heat capacity, which is either called S or C, multiply it by a mass, and multiply it by the change in temperature. The more massive the water sample you're using, the more energy it's going to take. The more that you want to change the temperature of that water sample, the more energy it's going to take. This is why, you know, if you eat potato soup that was very hot at the beginning, and it's going to burn your mouth, and you got to do that where you move it around real crazy in your mouth, because the potato in the potato soup has a lot of water content still in it. So it has a lot of energy because of water's high specific heat capacity. If we were to do the same thing with like a French fries we find go very cold pretty quickly because they are replaced with oil, right? The water in there is basically vaporized out, and oil's specific heat capacity is not so high. So keep in mind you can use either C or S for heat capacity. There's also molar specific heat capacity. So instead of a gram, it's a mole. And here we go. There's water's specific heat capacity. And here's that formula again, rewritten. Q equals MACAT. Again, you could have the S in there. Big old thing here is that your final temperature minus your initial temperature. If your final temperature is smaller than your initial temperature, then that amount will be negative, which will mean then your Q will be negative, which will show that your substance lost energy. So that's an important thing to keep in mind. There is one other type of calorimeter. Instead of putting a sample in water, sometimes you might use what's called a bomb calorimeter. This is something where you can actually have a reaction occur. So it's steel, and the chamber inside allows for you to basically explode samples and measure their heat energy. Well, the heat of the reaction is equal to the negative of the Q of the bomb plus the Q of the water. And here's the thing with the Q of the bomb. The Q of the bomb is basically just the heat capacity of the bomb calorimeter and the delta T. There is no mass because their mass is constant. Whatever you put in that substance you put in, and afterwards, since matter cannot be created or destroyed, there would be no change. So it is basically just the heat capacity of the bomb calorimeter. There's just no mass because there is no change in mass. All right, let's try problem or two. So how many joules are required to heat 32 grams of water from 25 degrees Celsius to 80 degrees Celsius? The specific heat capacity of water is 4.184. So there is going to give us our delta T, there's going to give us our mass, and there is our S. Is this an endothermic process or an exothermic process? Endo. We're absorbing energy. The temperature of the water is increasing. So we have Q equals MS delta T. The mass is 32 grams. The specific heat capacity, 4.184 joules per grams degrees Celsius. And then we've got 25 to 80, which is 55 degrees Celsius. Then you simply multiply those through. We get 7,363.84. Looks like 3 significant digits. So we get 7,360. That's joules because that's in kilojoules. If they asked you for, that's joules because that's in joules. If they asked you for kilojoules, that would be 7.36 kilojoules. Easy enough. If you're looking for specific heat capacity down here, then you simply need to rearrange the equation. Divide both sides by m delta T. And we get S equals Q over m delta T. Here's our m, here's our Q, and that's going to help us get our delta T. So basically we can put all of that in to our calculator. We get 435 joules over 3.4 grams and at 64 degrees Celsius. Now up here, remember, we had all of those units because if we take a look at this, grams and degrees Celsius are going to cancel out. Down here, none of those units are going to cancel out because we are solving for the specific heat capacity. And for that, we get 435 divided by 3.4 divided by 64. 2.0 joules per grams degrees Celsius. Some extra problems there to practice if you want. I could get the answers for those and post them. Questions so far? Let's take a look then at this specific heat demonstration here. Bring you guys over here. So this is a calorimeter. I've got some water boiling here already. Need to add some more to that because I don't think I'll have enough otherwise. So if we take a look right here, it says place in an insulated cup 50 grams of water that's at 100 degrees Celsius, and then add 50 grams of water that is at 0 degrees Celsius. So we need to make some water that's at 0 degrees Celsius. To do that, we need what's called an ice bath. So I've got my ice there and my water. Make sure we have enough water at 100 degrees. I'm going to go ahead and put another one of these on here. We need about 50 grams of it. All right. So I need to measure out 50 grams of water that's at 0 degrees Celsius. That's what we've got right here. I'm going to find, and I don't know if you guys can see the scale here. So I'm going to zero that. And I'm going to pour 50 milliliters roughly in there. and just let it keep going. Put a little more ice in there. Get it up to 50 milliliters, 50 grams-ish. Let's check our water here that just started boiling. Got a temperature probe here. So we got that at 99.2, 99.3. Here we go. $100. Oh, we're getting a little bit higher now, but I'm going to mix that up. It's going to be close enough for me. These Insta-read things are pretty good, but that's pretty close to 100. So we need 50 grams of it. So I'm going to mass out my calorimeter cup and zero that. Then we're going to add 50 grams of that water. Almost there. Can't get the hand in there. Morning. Lost hearing in my right ear today, so I got to go to the doctor later.
Michelle, have you talked to her?
No.
She texted me this morning and said she can't hear out of one of her ears.
Are you serious?
That's so bizarre.
That's weird that both of us have it at the same time, right?
Really bizarre. I'm definitely going to stay away from you.
Right? Yeah, that's kind of scary. So I've got about 50 grams. I'm with them real quick. I've got about 50 grams of the H2O at 100 degrees. We could measure that temperature again. I'm going to go ahead and measure this guy. Make sure we're close to zero. What do we expect the final temperature to be if we mix 50 grams of H2O at 100 degrees and 50 grams of H2O at 0 degrees?
$50.
You got it, right? That's what we would think. What are some problems with this? I mean, you
Room
walked
temperature.
to the lab. I wasn't able to move very quickly, right? Anybody?
Temperature of the room.
Temperature of the room. The amount of time that was off of the boiling, the hot plate, things like that, right? Well, we can see 40-ish. What's another thing? What else absorbed heat?
The vessel.
Yeah, this cup. And the fact that it was sitting in the room for so long because I wasn't able to pour that very quickly. Probably should have had gloves or some better apparatus to do that. The fact that that was the case means that it basically would have been, lost energy due to that. So we got about 40. Excuse me. So with this next one, I'm going to get the actual piece of metal in there weighs about 20 grams, 18.276. So what I'm going to do is I'm going to get 18.276 grams of water. Does it want that it wants that at 0 degrees too, doesn't it? Huh. That way we can keep that the same. Makes sense. So if we take a look here, we've got some water down here at 0 degrees, about 20. What are we expecting this time? You think we'll get about to 50 again?
No.
So we drop the piece of aluminum in there. And oh, stir around that. I had it, I lost it. Let's put our guy in there. Take a look there. Not even close to going up to 50, right? 17.5. So we went from 0 to 17.5. Even though the metal was at 100 degrees because it was in the boiling water. So we didn't even reach a fraction of what we did before, right? We didn't even reach half, I should say, because we got up to at least 40 with the other one. So then it says 100 grams of water at 100 degrees Celsius and mostly ice at 0 degrees Celsius. So last time we did this, we had just water, 50 grams of water at 0 degrees Celsius. So this time we want to actually get this ice. There we go there. What am I doing? I'm adding the ice to it. So I need to get the 50 grams of water in here. Should have probably brought a second calorimeter cup. See if I can do this better this time. So we have 50 grams of water at 100 degrees and 50 grams of ice at 0 degrees. What are we expecting here?
Under 50.
Under 50 for sure. We even saw under 50 though for water. Right? Do you think the 50 grams of water can heat it up above 25? What's the state of matter of the ice?
Solid.
You got it. So the particles are just vibrating. They're not moving very fast. They can't flow by one another. we have to put energy into that crystalline structure, that ice structure, in order to get those particles to melt. And that takes energy. You can see that we actually end up under 20 at 18.4 for that. Now we have the ability to mathematically calculate all of those things. But you know, we were just doing mental predictions and then the observations. We will be showing you tomorrow how to calculate what we would with that ice there. You share. Weird. So I didn't get that down. Hopefully you did if you were listening, but that's what I've got for today. You've got plenty of, this is one of the topics that I do have plenty of exercises or problems that you may work through. So I would use this next, 15 minutes to work through some of those. Otherwise, I do think that that's enough for today. I don't think that we want to, I know that sometimes I get these direct messages that say, slow down, this is a lot, that type of thing. So there we go. Look at that. What's that from? Some type of dye. There is one question. So it doesn't matter if the delta T is positive or negative, it will always be positive. So that is not true. If we take a look, this is increasing its temperature. So this is gaining energy again. And this is going from 21 to 85. Specific heat capacity, we would probably make that always positive if we had the option. But you can have, if something is losing energy, like for example, this right here, a 12-gram piece of iron is removed from an oven at 102 degrees Celsius and it cools to 21 degrees Celsius. How much heat in joules left the iron? If this just said how much heat was transferred, you might say it would be negative here. The fact that they say left, that could also be positive because you're justifying the fact that it did leave. So the sign is important for your delta T, especially if we were trying to calculate the amount of heat that were transferred between these two things. Because if we were doing that, the heat of one must be heat equal to the heat of the other. But one of them will be losing the heat, right? So its temperature, its delta T would be negative, and the other one would be gaining the heat. So if you're comparing this like this, the heat of energy from the ice to the water, one of those would have to be negative. Otherwise, your math's not going to work out correctly. And this is the problems that like we're going to be doing tomorrow and Friday. All right, if you have questions, by all means, stick around. Otherwise, have a great day. And hopefully, I did extend the time on the Unit 5 progress check. So hopefully you guys got in there and got that done. Take care.
Thank you, Mr. Jackson.
Thank you, William.